For our second tutorial for ECE297, we're going to continue with our standard template library. And this tutorial will start with STL iterators. Recall from last tutorial, we covered C++ templates. We have function templates and class templates. And we started the standard template library with the vector class from the containers library. And today we're going to look at iterators. What is an iterator? What operations can I perform with an iterator? And how can we apply the iterator to list? And how are lists different from vector in terms of iterator? So first, what is an iterator? An iterator identifies an element in the container, similar to a pointer that points to an element in the container. An iterator allows us to access an element in the container by dereferencing, also similar to a pointer. An iterator allows us to move between the elements in the container with similar to pointer arithmetic. So basically, iterators are classes implemented for STL containers to act like pointers. An iterator is restricted to only efficient operations. This means that if an iteration operation is not efficient enough for a certain container, like for a list, iterator plus 2 is not efficient, so it's just not implemented, so it's not supported. And I'll show you in the next few slides. So why not just use the array square bracket index to access elements, like in array and vectors? Operator square bracket implies random access. This means that given the address of the first element, we add index to that address will lead us to the element located at that index. And this is only valid for things like arrays, and that's random access. Random access is not supported by all data structures. Like for lists, we're only able to move forward or backwards. But in the STL, all containers have iterators defined. All of those are of different types. A vector int iterator is different from a vector float iterator, and is different from a list iterator. Now let's use vector as an example. We have already seen that we are able to access and modify any element in the vector using the operator square brackets and the index. We can insert a new element into it using pushback. We can query the size of the vector. All of the above have O1 complexity. And today, we're adding the two begin and end functions that returns an iterator to the first element and to the element following the last element for the end. So the end is used for bounds checking. For checking whether we're iterating out of bounds. Visually, my vector.begin will point to index 0. And my vector.end will point to 1 past the end. So my vector.end is not pointing to a valid element. Let's consider these cases and let's think about whether the operations are allowed. So case 1, we are declaring a vector of integer iterator, it, and assigning numbers. Numbers is a vector of integer, .begin. Who thinks this is allowed? Let's do a show of hands. Who thinks this is allowed? Who thinks this is not allowed? So the first one is allowed. We will save the iterator IT as the number slot begin, the first element, pointing to 1. Case 2, IT equals to 5. Who thinks this is allowed? Who thinks this is not allowed? Give me some reactions. We're assigning an integer into an iterator. The iterator is a class type, so it's not allowed. Case 3, IT++. Who thinks this is allowed? Who thinks this is not allowed? This is actually allowed because the plus plus operator is defined for iterators to move to the next element. Case 4, IT minus minus. Who thinks this is allowed? Who thinks this is not allowed? This is allowed, similar to plus plus, minus minus is defined to move to the prior element. Int x equals to dereferencing of IT. Who thinks this is allowed? Who thinks this is not allowed? This is allowed. Dereferencing of IT allows you to access the element that's pointing to byte IT. And the next two are conditions that are placed into the for loop, condition checking, and the if statements. If we check IT not equal to numbers.end, is this allowed? Who thinks this is allowed? Who thinks this is not allowed? Who's not sure? This check is allowed. This checks whether IT is pointing to the end bound of the container. IT less than numbers.end. Who thinks this is allowed? Who thinks this is not allowed? Who's not sure? This, again, is allowed. This checks if the iterator is before the end, which means that it's pointing to some valid element in the container. Now, case 8, dereferencing of IT equals to 27. Who thinks this is allowed? Who thinks this is not allowed? For dereferencing IT, putting 27 into IT, this writes the element at IT to 27. So this is allowed. And the last one, IT equals to numbers.begin plus 2. Remember, we're doing this with a vector. So who thinks this is allowed? Who thinks this is not allowed? Who's not sure? So this is allowed for the vector. So this will first get the iterator pointing to the first element. It will then plus 2, so moves 2 backwards, and then pointing to the third element. Therefore, if we're looping through a vector, we have two options. The first option is using indices. We go from index 0 to index 1, number slot size -1, and using the square bracket to access each element. And the second option is to use iterators. We start from iterator number slot begin. We stop when it sees number slot end, and we increment in each iteration. And we can access the elements by dereferencing. using star IT to dereference, which is similar to a pointer. Now let's get into our first exercise. So we have this extract negatives function. It returns a vector of int, and it takes in by reference a vector of integers. And what we want is that we have this empty negatives vector declared here. We want to use iterators to loop over the integers vector and add any element that is negative to the negatives vector using pushback. Let's go to this URL and complete the code under exercise 1. And we'll be back in 4 minutes. Remember, the iterators are classes that are written to be intuitively looking like pointers. Anyone needs more time? Need more time?
Plus IT, not IT.
So the IT++ and the plus ITs in the for loops are actually the same in current compilers. In some prior versions of compilers, plus IT is faster, slightly faster, but they're the same in current compilers, so it doesn't matter. Yeah. Okay, I'll continue. So your code should look something like this. We have the for loop. We initialize IT to be integers.begin. We check it's not at integers.end and increment IT. And inside it, we dereference IT to see the actual value pointing to. IT is pointing to. And if it's less than 0, that means it's negative. So let's push back dereference of IT into negatives. And now let's consider another function that instead of pushing the negatives into another vector, we remove the negative values from the integers vector. So we do the same for loop. Just inside, we check whether if it's negative. If it is, we use the vectors erase function that takes in an iterator. And what the erase function does is that it erases the element that's pointed by the iterator, and it will return an iterator to the next element. So in this case, we can't increment IT here. We have to increment whenever it's not erased, because erase will point to the next element. And internally, what does erase do? Say we have the vector like this. We have the process elements, we have the unprocessed elements, and we have IT right here. And we see that this is a negative value. So we call erase IT. The vector will keep the process elements the same, and it will copy over one by one the unprocessed elements to where the IT, the negative value was. And because the array is continuous, we'll have to copy every element after that. So that, then we will return the next iterator to the next element in IT2. So that is an O(n) complexity because we're doing the one by one copying. Then if the erase function itself is On, what is the complexity of the remove negatives function? Remember that we are looping through the entire vector, and we are calling the erase iterator whenever we're seeing a negative value. So what is the complexity? On squared. So the worst case, we erase n times in the looping over n elements. Even if we're not the worst case, it's still going to be on the same scale of On squared. And let's consider another form of container, a doubly linked list. So we have this structure of a linked list that can point to the next element and to the previous element. These are not stored continuously, so we cannot do random accessing. This only allows for bidirectional access to go to the next or the previous. But this one allows fast insert and erase because we don't have to do any copying other than just updating the neighbors next and previous pointers. So as a comparison between vector and list, they both can do begin and pushback and size in O1 time. Operator square bracket, which is random access, is defined for vector but not for list. Erase and insert for vector takes On. Erase and insert with an iterator takes On, but only O1 for lists. The iterator type for vector is random access. The iterator type for list is bidirectional. And this means that for vector, we're allowed to do plus plus minus minus plus 5. But plus 5 is not allowed for bidirectional. This only allows for plus plus and minus minus. So the iterator is then divided into 3 categories. The first one is random access, like vector. It can do dereferencing plus plus minus minus plus 5. Bidirectional, like list, cannot do plus 5. A forward iterator, like a forward list, is only able to do dereferencing and plus plus. And then in our remove negatives code, because list is proven to be more efficient than vectors, we'll replace the vectors with list. And the only thing we need to do is replace the vector with list and nothing else, because all the iterator operations are the same. So because of iterators, we can quickly switch from vector to list by just replacing vector with list. And that's one reason why iterators are so useful, because iterators are defined for all containers, and the operations are very similar between containers. And with list, remove negatives is On instead of On squared. Just be careful when you're switching from containers to containers, that not all code works interchangeably with all containers. Like if you're doing IT plus 5 for vectors, this will not work for list. Just in this case, we're only doing plus plus. Another trick is the C++11's auto keyword. So this keyword allows us to, instead of specifying a type when you're declaring a variable, such as integer, we can use the auto keyword so that the compiler will determine the type for you. Using an auto can help mainly saving with typing. And if you're switching types around frequently, sometimes the compiler is determining the type for you. But you should always know what the actual type will be. If you're doing anything confusing with the auto keyword, it could be very hard to debug. And the type is still static. So for example, if you're doing auto a equals to 2, and you assume that is a number, and later on you forgot that it's actually an integer, and you do something like a double operation, and it won't work. Because auto doesn't change with time. When it's first assigned a value, it's fixed. So to simplify the iterative code with auto, what we need to do is to replace the std vector int iterator with auto. So you don't have to type the iterator type over and over again when using iterators. You can just use auto it numbers.begin. Next, simpler still, we have the range base for syntax that's defined only for STL containers. So say we have a container, like a vector, and we can loop through it using for auto reference item column numbers. So the auto reference so that we can change the values and types automatically with a for loop. Numbers is the container name, and the for loop will loop from .begin to .end iterators. The for loop will dereference wherever the iterator is pointing to and give you the item variable. So that you can directly read and write into the item variable that's already dereferenced. So that you can directly output item without dereferencing anything. And this syntax works for all STL containers. And now I'll show you the demo for vector versus list erase function. Remember that the vector erase takes O(n) squared, and the list erase takes O(n). Look at the two source files. So we have a file called list erase and a file called vector erase. And what it does is that it includes the list header. It defines a list with n elements. And in this case, it defines a vector with n elements. It randomizes the entire container, and it does remove negatives with the same code. So the only thing different is the list versus vector names. Okay. Now let me do a make conf equals to release for timing. I'll time the vec erase first. This is O(n) squared. Let's go. Oh, that's the time for O(n) squared. Still running. 18.47 seconds. Now let's time list erase. 0.05 seconds for ON. And that's the reason why you should always be avoiding ON squared for larger data sets. Hey, QB. STL containers. We will be extending the containers to associative containers versus sequential containers. We're extending that further to unordered associative containers over an ordered one. So sequential containers are the containers that we have been looking at, like a vector is a sequential, it's a 1D array. A list is sequential, it's a 1D list. So now, given a vector, which is a sequential container, how can we find the value in the STD vector? The most intuitive brute force way. How can we, yeah. Yeah, you linearly search. So the STD find function is defined in the STL to do a linear search that loops from myvec.begin to myvec.end and searches for a single value. And it will return the iterator to where it finds the value. And it returns at the first appearance of the value. We have the second option, which is to sort the container first, and then we can search with something like O log n using binary search. But this could be difficult and error-prone to program. And also sorting the container itself could take more than ON time. So if you're just doing it once, it's not worth it. But what data structure is inherently ordered? Have you covered any data structure that is ordered by itself? Yeah. Binary search tree. From ECE244, we have a binary search tree that is inherently ordered, where the left node is always less than the middle node and is always less than the right node. And in the STL, it's implemented into a map so that you don't have to write a binary search tree. So the STD map is self-balancing BST. Therefore, it's guaranteed O log n time to find, insert, and erase. STD map uses STD pair to store its elements. The first element in the pair is the key, the second is the value. And map is sorted based on the key. An example of the map could be a domain name lookup server. What this does is whenever you are typing in a URL into your browser will first query the domain name server using the URL like ug152.ecg.utoronto.ca. It will ask the domain name server, I have this string. Can you tell me which IP address I should actually be going to? And inside the domain name server, it will look up the string and return the IP address as an integer. So inside the domain name server, it's a binary search tree that stores pairs of strings as the key and integer as the value. Inserting into the map. So first, using the map, we'll need to include the map header. And then we create a map specifying the key and value because maps are templated. The map is called DNS lookup, and we have three options to insert. The first option is to manually create a pair of string and integer, and we use the pairs constructor to make the pair of google.com and its corresponding IP address and insert that into the DNS lookup. The second option, you could use the make pair helper function by SDL. So this will return the pair depending on what you give it. And you can simplify the code by using auto. And we insert. Option 3, even simpler. We can skip the auto echo part and we directly pass in the make pair into the insert. That's insertion. If we want to search inside the map, what should we use to search, the key or the value? So who thinks it's the key? Who thinks it's the value? It's the key. Because remember, when we are querying the domain name server, we are giving it the actual string of the URL. So we call the find function in the map container. Then the find function will return an iterator. How do we check if the key was found or not found? Any idea? So the find function will return the iterator to wherever the value is when it's found. When it's not found, the find function will return DNS lookup.end. So we check whether IT equals to DNS lookup.end, and if it is found, we can dereference IT using the same syntax as pointers. And if it's equal to DNS lookup.end, it's not found. So IT points to the entire node, which is a pair. It's not the key or the value. So you have to dereference it and access the first and second element of the pair to access the value. Exercise 2. So we have the STD map. And let's use iterators and a for loop to print out all of the nodes in the STD map. So what we want is key column value on each line. Let's go back to code board and complete exercise 2. We'll be back in 4 minutes. So this is the case where the index approach does not work. You have to use the iterators. Anyone needs more time? Or I'll continue? So this should be how your code should look like for auto, so that you don't have to type the entire name of the iterator type. IT equals to DNS lookup.begin. It's not equal to DNS lookup.end, and increment every iteration. And in each iteration, we output it.first, it.second. And as you should already notice, this is the output, and it's already sorted by the key. Even if it's inserted with a different order, the output is sorted. And this is because map iterator advances as an in-order traversal of the binary search tree. And in-order traversal means left, then center, then right. And because it's a binary search tree, in-order traversal is sorted. So my map.begin will point to the first element, the leftmost element that is the smallest in the binary search tree. And my map.end is pointing to one past the rightmost element, which is the largest. And the in-order traversal will start from the leftmost and do 1, 2, 3, 4, 5, 6, then end. And when we call the find, it will return the iterator to whichever element that's being found, or it will return my map.end. Now let's consider another case. Say we have a map that's storing the salary of employees, and we have 2 employees with the same name, John Smith. When we're using the binary search tree, maps are only defined for single unique keys. So the second insertion will not happen because the key already exists. And when we do the find John Smith and output, it will only find the John Smith with the first, that's first inserted, which is 45,000. So what do we do in this case if we want both John Smith? We look into the C++ reference website and the containers library and see if we have any options to store duplicate keys in the map. And if we go look into the website, we'll find something like a multi-map. So a multi-map is a map that can store duplicate keys, so that the second insertion will happen with a multi-map. But when we call the find function, it's still going to only return a single iterator. So that's not what we want. And let's look back into the documentation again and see if multi-map provides any other options. Then we will find something called equal range. The equal range function will then return a pair of iterators that gives the range of the entries matching the key John Smith. And the 2 iterators are the begin and end iterators of the range. Remember, the begin iterator is always pointing to the first element. And the end element is always pointing to the element past the last element. So our new for loop will look like this. We have the range, that's a pair of iterators returned by equal range. We start from range dot first. We stop when we see range dot second. And we increment the iterator. And we can output all entries within the range. Like this. Why does equal range work then? Remember, this is a binary search tree. So the keys of the same value are guaranteed to be stored together in a continuous range. So range.first returns the first element matching John Smith. Range.second returns the one past element, the element that's one past the last John Smith. Is that okay? Yeah.
Both of the John Smith would not be like next to each other, but if there would be like some other like element between them, that would not be the same, then what would it be?
Yeah, this is a binary search tree, and the same keys are guaranteed to be stored together. There are other containers in the STL that we're not going into details about. We have the map, multi-map, and all of those have the same O log n time for find, insert, and erase because they are both binary trees. We have the set, which is also a binary tree, but use it only if you need keys and not their values. So set is just a map that stores only one value, not the pairs. We have the unordered map that can do O one time for find, insert, erase. And this is much faster than the other ones, but it's not ordered. And it cannot be ordered in any way. So use it when the order doesn't matter. And we'll be talking about this later. Containers, other containers, we have queue, which is useful for accessing first in, first out data. So you only want to access one data at a time. That's the one that's pushed in first. Priority queue gives you O1 time for accessing the largest by default, or you can turn it into the minimum element in the queue. And push takes O log n time because priority queue is a heap. The stack does last in, first out, or first in, last out. A DQ is similar to a vector, but is faster for insertions and deletions. Map versus unordered map. Ordered versus unordered. A map, which is a binary search tree, is ordered inherently, and it takes O log n to find an element by key. And it's able to compile for any key type that has the operator less than defined by default. Or you can configure it to use another operator, comparison operator. Unordered map is implemented by a hash table. So hash tables are very fast to find the key in O1 time. And it's compiled whenever the key type has the hash function defined in the STL. Unordered map is never going to be sorted because it's a hash table. So our course expectations, we will not be teaching everything in STL to you, and this will be our last tutorial focusing on STL. But it is and will be very useful, so we expect all of you to be able to research in the STL using those references and to make your design decisions of which container to use in your project. Now I'll demo the second demo, which is map versus unordered map. Let me post this one. So we have few source files. Also, we have a very large N. And in both cases, we are going to populate the map or the unordered map with N elements. And then we'll be searching randomly for 10 times N keys. Go to the terminal and make using the release configuration. Remember that map is a binary search tree, so it takes O log n time to insert and search. So let's time the map first. 0.36 seconds. That's the time for O log n. Now let's time the unordered map. 0.16 seconds. That's for unordered map. So we can see it's 2 times faster than the map. And this is typically what you will get for comparison between O log n and O1. O log n is typically a very good algorithm, but if you can do O1, always do O1. O1 is the fastest you can get. Is that okay? We have the third one for STL algorithms, and that's it. Anyone needs a break? If it's okay for everyone, I'll just continue. STL algorithms. So what we've been talking about are in the containers library. And now we have the algorithms library that provides a lot of useful algorithms for you. And we'll be using the find and the sort functions as examples. First, finding elements. You have a collection of data and you need to find a specific value in the collection. The option 1 is to write a for loop to go through each element, and on each iteration you compare. And when you found the element, you finish. Option 2, use the STD find function that's given to you by the STL. This does the same thing as option 1, exactly the same thing. This takes in an iterator to the beginning and end of the container. It returns the iterator to the first match and it exits. So we prefer the second option over the first because it's less typing and it's easier to understand the intent, so that you don't have to read through an entire for loop and realize, oh, you're finding something in this container. The find dictates the intent in its name. And we reuse the well-tested code from the library so that you don't have to worry about needing to debug inside the for loop that you just wrote. And the syntax for find is like this. We use the STD find helper function that's included from the algorithm header. And we pass in the begin and end iterators for the range that we are searching for. And lastly, we have the value that we're searching for. And the compiler will determine the type if you're using auto keyword for the iterator, because find returns the iterator. Then we check if iterator returned is not collection.end. And if it is, the find failed to find the actual value. If it is not the end, you can dereference the iterator and do whatever with it. Now, exercise 3. Let's go back to codeboard, and we're given a vector of collection of integers. We want to use find and iterators to return true only if the first element is 1 and no other elements are 1s. So we want to check for 2 conditions. One is the first element is 1. The other one is the other elements are not 1s. Use find and iterators. And we'll be back in 6 minutes. Remember that you don't need a for loop if you have the find function. Anyone needs more time? I'll take that as a no. So we should write something like this. We first read in the first element. We first read in the first element. And the first condition is whether it's 1. And then we've called a find function for first element plus 1 to end. Search for 1. So the second check is check whether IT is collection.end, and we return true only if the first element is 1 and IT equals to collection.end. Otherwise, false. Is it good? We have other functions in the algorithm library. We have the minimum, the maximum, the sort, the find, the swap, and the count function. The count function counts the number of elements of a value in a given range, defined by its start and end iterators, and many more. Now, as an exercise for researching in the STL library, let's find the definition of the sort function online. You can find it in any website. And see if you can answer these questions. So for the simplest call to sort, how many arguments does it accept? And what are the requirements on the arguments? The simplest call. I know we can get more arguments, but how many? Anyone with an answer? For the simplest call to sort, how many arguments does it accept and what are they? 2. And what are they? So begin and end of the same type. And what are the requirements on the type of the arguments? What should the type be? You just said begin to end, so there are iterators, right? The 2 arguments. Like only the arguments, not the return. They have to be the same type. And what kind of type? Iterators. What kind of iterators? Random access iterators. They must be random access iterators so that the range of elements are stored together like a vector. Something like a hash table doesn't work. Something like a list doesn't work. How are the elements compared? By default. What is the operator used to compare the elements by default? Yeah. The less than. Yeah. Operator less than. And what is the complexity of sort? Yeah. N log n. And all of these you can find on one page. And then how to write the sort function. Say we have a vector of numbers. We can write the sort by first including the algorithm header. We call sort directly with numbers.begin, numbers.end. And this by default will sort using the operator less than. And you can test this code at home to see what it's outputting. And that's it for today's tutorial. If you have further questions, you can ask me. I'll be here for that. Thank you.